Great.
All right, good afternoon. Let's get started with the physics seminar today. It's part of the Eddie and April Lucas funded Physics 4 seminar series. This semester, we actually have a few speakers in person, even from out of town, coming to Wichita again. We also have other speakers just on Zoom and a few speakers in person, but without any travel expense. Aditya Sharma is one of our own graduate students. He was awarded the Hall Schneider Fellowship for summer research this summer and will present today the research he did over the summer with Professor Ferguson. So welcome, Aditya. And we can share the screen. And we should be ready to go. All right.
Hello, everyone. I'm Aditya Sharma. So I'm a graduate student here in the physics department. I work with Dr. Ferguson in the astrophysics group. And I was a Hall Schneider Fellow for summer 2021. And I'm here today to present my research during the summer. So obviously, tidal effect of low temperature opacities on stellar isochrones. So yeah, I will first go through some basics, and then we'll move on to research.
Click on the slide with the mouse.
Okay.
Maybe I just hang on.
Okay, so first we're going to talk about stars and their structure and their evolution. So first, stellar structure. We know in the cores of stars, we have high temperature, and due to that, we get nuclear fusion, where hydrogen is being converted to helium. Now, stars, for most part of their lifetime, will be in hydrostatic equilibrium. So that equation right there, so that is the hydrostatic equation, which, so this term is from the gravity. So the gravity of a star want to collapse the star into the center. So it's going inwards, while the pressure, the radiation pressure generated from the fusion is outwards. So they are in opposite directions. And each layer of a star, when it's in hydrostatic equilibrium, this the pressure due to gravity and the pressure due to the radiation will be equal but similar. So all the layers of the star are in hydrostatic equilibrium. So basically that term disappears because you don't have any acceleration. So that acceleration term disappears, becomes zero because it's in equilibrium, so that we get this. So yeah, that is what we generally call a main sequence star when it's in hydrostatic equilibrium. Now, obviously, it's a nice diagram. You know, you showed someone when you are being introduced to stellar evolution. So I'll use this, and obviously we have molecular clouds of gas and dust from which we get protostars. Now, when there is sufficient temperature in the core to start hydrogen fusion, those protostars go from pre-main sequence to main sequence. So that star in the previous slide, that was a main sequence star. So this is also a main sequence star. So you have brown dwarfs, which are basically failed stars. You can see, so if the mass of the star is below 8% the mass of the sun, it will never start hydrogen fusion in the core. So that's basically a failed star. So the anything greater than that will start hydrogen fusion, and we get the main sequence. After that, when the hydrogen is exhausted in the core, you have an inert helium core now. And hydrogen is being burned in a shell around that core. So it's a hydrogen shell around the core where the energy is being produced. So that is when stars become red giants. And these are stars between 0.08 solar mass to 8 solar mass. So between this range, stars become red giants. Obviously, the lifetime of a star depends on its mass. The heavier the star is, the more massive it is, the shorter it lives because it exhausts the hydrogen faster. So we have the red giants. which obviously become planetary nebula. There are actually a couple of stages before that. You also have the horizontal branch, which is when the helium, the inert helium core is not inert anymore. The helium is being fused now. So the energy is being produced due to helium fusion. So that is.
Helium is typically inert and it's reacting.
Now you need higher temperature to fuse helium in the core of a star. So for in the red giant, when it's in the red giant branch, it's not high enough. So when there's a buildup of helium over time, the temperature gets high enough, and then the helium starts burning in the core. So that is when they jump to the horizontal branch. And we'll see these all these branches later in some diagrams, in some plots. After that, helium also exhausts, convert now. So now we have basically a carbon oxygen core, and you have a shell of helium over that core, and you have another shell of hydrogen over that core. And sometimes what will happen is they will sometimes it's the hydrogen core which is producing more energy, sometimes the helium core. So those are called stellar pulses. Again, we'll look at that later in the presentation. So yeah, after that is planetary nebula, which means after the AGB, which is the asymptotic giant branch. So after that, you get planetary nebula. All the layers of the star have been, basically, it's just a core that's left, and all the layers have been blown off. And in the end, you have, because there's no fusion anymore, so there's no hydrostatic equilibrium, so the gravity collapses the star. And it's only the electron degeneracy pressure which prevents it, and it becomes a white dwarf. So for that, the mass of the core needs to be below 1.44 times the solar mass, and eventually they become black dwarfs. But no white dwarf is a black dwarf yet, because that can take several billion years, longer than the age of the universe. So this is what I'm focusing on, really. These stars between, well, all the stars up to 8 solar masses. Obviously, we have more massive stars, and we have, these become red supergiants instead of red giants, and they don't go planetary nebula. They actually do types of supernova. They just blow off their layers. When there's no fusion going anymore, so they can go all the way up to iron. They can fuse up to iron. But after that, there's no energy being produced, so the gravity collapses. They are so massive, the core is so massive that the electron degeneracy pressure cannot prevent the collapse. So it's actually the neutron degeneracy pressure which does that. And the star is actually contracting at almost a relativistic speed. And then when the pressure stops it, it kind of goes, it rebounds, and it blows off, which is a supernova, a type 2 supernova. And after that,
you have equations that relate the counteractivity. You have an equation that calculate what that strength of that
supernova,
where it starts going outward instead.
Oh,
Well, it doesn't matter. Sorry.
Yeah, that's we're not really focusing on this. I'm just talking about it. We're really focusing on these stars here.
Okay.
Yeah, but yeah, that's interesting though, supernovas. And after that, we have neutron stars if the mass is below the Tolman-Oppenheimer-Volkoff limit, the TOV limit, which is around, I want to say around 3 solar masses. So the initial mass needs to be around 40. And if it's above, it becomes a black hole, because even neutron degeneracy pressure cannot prevent it from collapsing. That's stellar evolution. Now we're going to talk about opacity. So opacity can, another name for it could be opaqueness. So how opaque something is, how much radiation or light is being transmitted through something. So that's opacity. Now, obviously, we're talking about stellar opacities. So that's the material in the star. There's this nice picture which shows the random walk of a photon, which is generated as a result of fusion in the core. And actually, it's produced as a gamma ray, but is scattered countless times before it gets to the surface. And it's not a gamma ray anymore because of all the scattering, loses energy. And it can take about 100,000 years. I think the mean is around 30 or 40,000 years, but it can take up to 100,000 years. And the yeah, so obviously the extent of how much that radiation is scattered is characterized by the opacity, how opaque the materials are there inside the star. So the opacity will depend on the density, on the temperature, on the composition of the material in the star, and also the wavelength of light. Okay, sources of stellar opacity. We have these different sources. We have the bound-bound transition. Again, this picture tries to explain some of them. So we have the bound-bound transition, which is when you have an electron jumping from one orbital to another. So it can absorb a photon. It can go from a lower energy level to a higher energy level, and that's bound-bound transition. It can also happen the other way, from a higher energy orbital to a lower energy, and this time it releases a photon. So that's bound-bound. You have bound-free, which means basically photoionization. So a photon ionizes an atom, which means an electron is released. So that can happen. Again, opposite can happen as well. That's called recombination. Free transition is when you have an electron which is accelerated or decelerated around an ion, releasing or emitting a photon. When it's slowed down, it actually releases a photon. That's called Bremsstrahlung, literally meaning breaking radiation in German. So that's free transition, and you have electron scattering, which is just when a photon is incident on an electron. And that is a little bit different because that doesn't depend on the wavelength. The cross section is the same for all wavelengths for electron scattering. And you have the H- sign, which means you have a hydrogen atom. You also have another electron there. Now on the other side of the ion, so two electrons on the opposite side. And because the electron, this extra electron, is closer to the nucleus, it has a net positive charge on it. So that's the H- sign, and it has a very low binding energy. So it compared to the other ground state one, so it has a very low binding energy. It can be ionized pretty easily. So these are the 5 main sources. There are some others, minor ones, but yeah, these are the 5 main ones. This is Kramer's opacity law, and this is it can be called a way to define these opacities, but these are not really used anymore. These are just something that were used a long time ago, 50, 60 years ago. And it's so it's sort of this form. This is a relationship between the opacity, the kappa, and the density and the temperature. So we can see this relationship here for the bound-free opacities, for the free opacities.
This also applied to the traditional optical opacity, or visible wavelength light.
Yes. Okay, okay, and these G sub EF, G sub FF, these are Gaunt factors. These are quantum mechanical factors that are there. Also T here is another correctional factor. And Z and X are the mass fractions of hydrogen. X is a mass fraction for hydrogen, and Z is the mass fraction for metals, which is everything except hydrogen and helium. Those are called metals in astronomy. And again, we can see it's a bit different for electron scattering, no dependence on, it's similar for everything. So it's just dependent on mass fraction of hydrogen. This is the equation for the H- sign. And this is, these are just semi-empirical, very old. And you can see there's no equation for bound, because there's no one single equation that can define all the contributions. So what we are really using is Roslyn mean opacity, and it's a Planck distribution, and you can see it's average over all frequencies or wavelengths. So now we had this wavelength dependence here that's gone because we are doing this now, and it's inverse, so it weighs more heavily where the opacities are lowest. And all the opacities that will be discussed further are Roslyn mean opacities. So this is what we are using. Now, opacities these days will be stored as opacity tables. And we, for this study, used the ATOP, which is the Atlas Opacity Program, and the Phoenix Stellar Atmospheric Code. So these are codes which are used to produce those opacity tables. So we use these. So an opacity table will have, for example, number of temperatures log T's, number of densities log R's, and you're gonna get a bunch of opacities there. So, and for different mass fractions, right, different X's and Z's.
Are they huge books? Or is it that many things involved? Not huge, not huge books. Okay, because I've seen huge books on other mathematical things. Sorry.
Yeah.
Oh, okay.
And you have to use an initial abundance set data to produce those opacity tables, and there are several. So, and these are done through spectroscopy. And these are the sources that we took those abundance set data from. So we used Greves and Sowell from 1998, Greves and Knowles from 1993, and Asplund et al. And actually, Greves and Sowell were co-authors there as well. But for the sake of simplicity, we'll call this A09 or A09. And this is GS98, this is GN93. Sometimes it's called AGSS09. But yeah, so something about ATOP. It was originally written by Robert Kurz in 1970. There were many more updates after that. So it makes assumptions such as local thermodynamic equilibrium, which just means there's no heat transfer. If there is, it's pretty slow. You can assume it's in thermodynamic equilibrium. You have chemical equilibrium for all species. It uses pre-computed molecular line data to compute opacities, and it has 6-grain species, 30 million molecular opacity lines. So that's just some information about ATOP. And now we're going to look at Phoenix and how it's different. So it is a much recent, much more modern code. It was originally written by Peter Hauschild in the mid-1990s. It has more frequencies than ATOP. ATOP is around 9,000, and Phoenix has around 24,000. So yeah, it's have more frequencies, makes it much more accurate in non-solar compositions. And instead of using these pre-computed molecular line data, it uses large line lists for molecular opacity computation. So the equation of state for these two are different, uses different ways to do the thing. It has more grain species, 31 to 6, and more molecular species, several hundred. Also, all these things makes it better in calculation of low temperature opacities than ATOP. But there are people who will still use ATOP. In 2021, there have been citations. MESA is what we are using to produce these stellar evolution models. So it's a one-dimensional stellar evolution code, and open source, anyone can use it. Can be used for a wide range of environments. You can do several things there, different conditions. There are a lot of things that can be inputted. And it uses, employs parallel computing so that everything can be done faster. It uses several processors. So it can also produce these plots. There's this thing in MESA called PG plot, which is producing essentially a screenshot of data at a time. And there will be several important plots there as well. And you can create your own grid of plots that you want. So it can do that. And because it's producing a screenshot every 5 models or 10 models, you can combine those and make it into a video file as well. And obviously, we have history files, which have all the data of the star during its lifetime, for example, luminosity and temperature, and everything. There's like 70 or 80 columns of data that are in these history files. You also have profile data files, which will be the data of the star during a moment in time. So like a model during that screenshot, basically, what is going on in the star. So that's a profile data file. Some of the inputs that you can make in MESA physical assumptions such as rotation or stellar winds and stuff. So you can change this stuff. You can obviously change the initial mass of the star. You can change the opacity tables, the mass fractions, starting conditions for different stages. A 1 solar mass is going to evolve differently than a 5 solar mass. And when they change their stages, it's going to be a little bit different. So you can control that. You can control everything. Outputs, total luminosity. You can also get the energy output for example, due to just hydrogen burning and due to just helium burning. So PP chain reaction and CNO reaction, which are going to produce helium through hydrogen burning. You can just do that, or other elements as well. So you have that. You have effective temperature in the output. You have mass and radius for different layers. As I talked about, you can get layers of different elements. For more massive stars, you will get like hydrogen, helium, new carbon, oxygen, and you get different layers at the end. So it can tell you about that. Thermal power from different reactions, as I said, different reactions are happening, PP chain reaction, proton-proton chain, or CNO cycle, and all these things are happening. So you can just find what is the thermal power from that reaction alone. Mass loss happens, especially after the main sequence, especially in the AGB phase, a lot of mass is discarded. So the mass loss is another output. And this is what a history file looks like in MESA. There's a bunch of data. It goes all the way up to, I don't know how many columns. And yeah, you can see model number. So these model number you can see are not a function of time, really. You can see the time doesn't change linearly or anything. It doesn't change as with the model number. So basically what MESA does is it will make models when it sees something is happening within the star, something is changing, something interesting is happening. So because during the main sequence, it's pretty much stable and nothing is happening. So it will just go over the main sequence pretty quickly. And then when it gets to a red giant branch, gets to the AGB, the asymptotic giant branch. Yeah.
Because nothing's happening that's worth noting.
Yeah. So that's the main sequence where it's in hydrostatic equilibrium. So yeah, it goes, so it not skips, but it goes over the main sequence quickly. And then red giant branch, it takes a long time. For the red giant branch, takes a long time. For the stellar pulses. Okay, so yeah, star age, star mass, and all these things is the data. So if you want to plot data, you could just simply, if you want to see something, for example, what is the energy output from hydrogen burning. So if we want to see that, we can have this diagram simply from the file. And this is log LH, energy output due to hydrogen burning. Model number, so why I did model number? Because if I did time, the main sequence part was going to be, all the way till there. And this last part where you see the pulses happening would be just so scrunched up, you wouldn't see it, because those happen very quickly relative to the age of the star. Yeah, so that's why we have model number. And this first part is the main sequence here, about till, I think, around 1,000 models. And then after that, we get to the red giant branch. So you can see hydrogen burning is the main source here. It's a major source of fusion of energy. And after that, we get this dip here. And because this is a dip.
Is that red, green, blue?
That is a red giant branch.
Oh, sorry.
Yeah, that's a red giant branch. I should have mentioned that.
Sorry.
Okay, so this dip is now because now helium starts burning, and that's the main source of energy, and that's called a blue loop. And that's majorly for stars that are large, bigger than 2 solar masses, 2.5 solar masses. So that's a blue loop. They grow hotter, and then they just go back. So again, it's hydrogen burning, but you can see at certain points, you have these, and obviously the next part is AGB. So that's the asymptotic giant branch. And now you have these dips here. What these dips are, these are called stellar pulses. So what is basically happening in slightly more massive stars than the sun, what will happen is you have this carbon oxygen core, you have the helium shell over it, and you have the hydrogen shell over that. So hydrogen shell is producing the energy. As you can see here, is the hydrogen output. When it drops, what is happening is because that hydrogen burning is producing helium, there's a buildup of helium, and that is able to ignite that shell. So that's called a helium flash. And for a small moment, small moment for a star, what it will do is it will burn helium for a while and then go back to burning hydrogen from that outer shell. So those are called stellar pulses. And during these,
and you can calculate at what point it would come into effect and then stop happening.
the stellar pulses.
Yeah, can you calculate when they're going to happen, like critical mass or whatever?
Yeah, we can calculate that.
Sorry.
Yes. So they all happen in the AGB phase after the horizontal branch or the blue loop. So yeah, we have these stellar pulses. All these are stellar pulses. What will happen is the luminosity will be very high during these times. So its luminosity increase significantly and can be observed very easily. So these are called stellar pulses. Okay, now what we are using to look at the data are HR diagrams. So Hertzsprung-Russell diagrams are the scatter plots. So you have energy output per time or luminosity or absolute magnitude on the y-axis, and you have effective temperature or stellar classification. It can be color index, something that tells you about the temperature of the star on the x-axis. And so this is, I think, yeah, it was developed by Hertzsprung and Russell in 1910. And this is one of the first, I think this is from Russell in 1914. So this is one of the first ones.
Do you have something that tells what the different types of plots are?
Well, yeah, that's the next slide. So this is one of the more modern ones that we see in textbooks. And you can see, again, spectral class, or it could be just, probably can see it, but it's temperature there, absolute magnitude here, or luminosity. So our sun on this HR diagram would be somewhere around here. It's a G2 star spectral type. So it would be somewhere around here. Now, this is the main sequence, which we discussed earlier. After that, they become red giants, and they move like this off the main sequence. After that, it doesn't show it here, but we'll see that in the next slide. We have the horizontal branch, and then we go again to the asymptotic giant branch. And void dwarfs are down, all the way down here. You have some supergiants, which we didn't focus on in the study. So this is a much more modern HR diagram.
What I was asking about was the X and the O versus the large O and the points. There were different types of points on the previous one.
This one?
Before this. See the circles or X's?
Yeah, he was probably observing certain type of stars. So he may, that's just.
There's no notation to tell what the X's are.
Yeah, this is one of the ancient ones. So this makes more sense. Okay, so now on the left-hand side, we have this HR diagram, which tells the evolution of a one solar mass star like the sun. So main sequence here ends, we get a subgiant branch, and then after that, we have the red giant branch. So this is a red giant branch. We can see the temperature is decreasing while the luminosity increases significantly. And after that, we have the horizontal branch. It goes down here. And then after that, the AGB, the asymptotic giant branch. And after that, we go to planetary nebula. And then it doesn't show it here, but it goes something like this to white dwarf. So this is all those stages that I talked about earlier on an HR diagram. So just on an HR diagram, if you know the mass of the star, you know the position of the star, you know how old it is, you know what it is doing. And this is on the right-hand side, we have, so again, it's basically this diagram here, the yellow one. And for 2 solar mass, it looks like this. For 5 solar mass, it looks like this. So you have different, because different stars of different masses are going to evolve differently. So you have these different shapes of HR diagram. We really focused till around 5 or 8 solar mass, really. We didn't discuss. We are not going to discuss these. All right. So as I was talking about the video files that we can create from Mesa, this is one of them.
Why don't you hit the X on that little? Get out of the way.
Yeah.
There you go.
All right. So this is the video file created from a large number of screenshots. So I think this is around 40 seconds. So we can see that. So this is from one solar mass star. The upper diagram is obviously temperature versus density profile for the star at any given time. The lower left shows the HR diagram, and the lower right shows the core temperature versus core density. And there's a bunch of data, which you can also see in the history file. Yeah, probably need to hit that. So we can see already of the main sequence, already in the red giant branch, goes over main sequence very quickly, spending a lot of time on the red giant branch. Lots of models there. You can see the model number going up, and still on the red giant branch. All this data is available in the history file, so yeah, it's a bit messy here. And okay, now it's moving down. It's moving down to the horizontal branch. That's the horizontal branch now. And now it's going to move up again to the asymptotic giant branch. Now goes planetary nebula and then white dwarf. It took about 5,900 models for this. Depends.
It's kind of like everything just happened at the last few.
Yes, yes, everything, because the last stages are very quick compared to the rest of the line. Main sequence is by far the longest stage. Okay, what we did during the summer. So created several ATOP and Phoenix opacity tables. So we produce opacity tables from both the codes with different base abundance values. So we had GS98, GS93, A09, etc. We produced several Mesa runs from these different opacity tables for comparison. So you want to look at, if someone is producing an opacity table from Phoenix or ATOP, and if they are getting completely different results for their, from their models, then it's a bit of a problem because you don't want that. It's just a different code, but it's still be doing pretty much the same physics. So we really are looking for a kind of a null result. If there are differences, then we need to look at that.
I have to agree, or something's wrong with one or the other.
Yeah. We use interactive data language, or IDL. That's a data analysis programming language, much like MATLAB, really only used by astrophysicists to plot data from history files. So that's what we used. And some of the scripts for Mesa, so the Mesa, we saw the Mesa history file. Some of the scripts were written by Rick Townsend, I think from University of Wisconsin, Madison. And some were written by Lynn Buckley, who was a student here. They graduated in spring. They were also the other student in the astrophysics group. So they wrote some scripts for the HR diagrams. And this really, this little part here, this took a long time to write those scripts for isochrones, which we'll discuss later. Okay, here we have some results. So this is the one solar mass star produced with Phoenix opacity tables, and the abundance set was GS98, gravity sol 98. So we can see this again looks very much similar to the HR diagram we saw earlier for the one solar mass star. You can see the main sequence here, this subgiant branch, giant branch, horizontal branch, and the AGB. So we can see all the stages here. If we compare it with GN93 now, so we can see that they are not exactly the same. There are some differences, not too many though. They are pretty close, very minute differences. If we add the A09 one, so that's a little bit different. There might be some differences here. Those are completely numerical. There's no physics, different physics going on there. So the A09 one is a bit cooler everywhere, especially so after the main sequence, especially during that red giant branch. That's a bit different, the green one. So these are all produced with Phoenix. If you look at the same abundance sets and the ATOP opacity codes, now again we see that trend. If you just compare these two diagrams, these look pretty much the same. But again, we have this trend here where A09 is a bit cooler in the red giant branch. And we can see here during the main sequence, all three pretty close, but after in the red giant branch, the A09 was very different.
It seems like in the final phase, they're actually hotter to the left.
Yes.
To the left. Well,
Here.
Just like,
Yeah, what's the most visible difference seems to be in the red giant branch for now. So this is comparing Phoenix and ATOP runs, the same abundance data from GS98. Again, there are a little bit different. Again, the difference is really in the red giant branch. So it's the same abundance set, but Phoenix and ATOP, so two different opacity codes, giving us slightly different results here in the red giant branch. And this is the HR diagram for 5 solar mass star. So this again will look different than a 1 solar mass star. You can see here, this is the blue loop that I was talking about earlier, where it grows hotter for a while, then goes back, and this is the AGB phase. Now, as I said, stars that are greater than 2.5 solar masses will do stellar pulses as well. So those stellar pulses start here, and you can see it's starting to do that. Although I stopped these runs at about this moment. So if you can let this go on, I think it takes about 66,000 models to turn it into a white dwarf at the end. It can take a long time, and that can.
And does the pulsing dampen? Like, does it lessen? Does the pulses lessen? Does it dampen? Or
Increase.
Increase. Oh,
Yeah, they increase. So yeah, the pulses, yeah. So yeah, but if we just look at again, it's a bit different in the giant branch here. But after that, in this AGB phase, in the stellar pulse AGB phase, if you just zoom in at that part, we'll see they are again different. So again, at these stages, the red giant branch, asymptotic giant branch, where interesting things are happening, things are different. So that is, yeah, that was the HR diagrams. Now we're going to look at isochrones, what isochrones are. So we looked at HR diagrams. You have luminosity versus temperature. Stellar isochrones represent a bunch of stars of different masses, but the same age on the HR diagram. So that's what stellar isochrones are. Now, one might think, why would someone do that? Because different masses evolve differently. Why put them on the same diagram? It's because if you want to know the age of a certain star, you cannot do it. You cannot do it for this one star. You have to look at a population of stars. So when we see clusters, we have, yes?
Is it relative? Is that why?
No, because you have these clusters. You have globular clusters, you have open clusters and galaxies. Those clusters, all the stars in those clusters are formed at the same time. So because they are formed from the same clump of interstellar gas dust, they form at the same time. They are different masses, obviously, but they form at the same time. So that is why we're doing this. And all these curves, so this is what a curve is supposed to look like for 10 billion years. This is for 1 billion years, and so on, these different things. And this one goes higher for 5 million years, because there are some stars which live very short, but they are very luminous as well. Those will be the more massive ones. So yeah, they're used to determine ages of clusters in and around galaxies, and all stars in cluster are roughly the same age. So that's why stellar isochrones are important. They're used for population studies. And one solar mass star with ATOP and Phoenix opacity. So this is basically the same diagram as before. There's literally no difference, but now we have two stars here on the diagram at 12.4 billion years. So this is after the main sequence. This is a one solar mass star like the sun, so the main sequence lasts for about 10 billion years. After that, we have the red giant phase and the other phases. So if we look at those two stars at 12.4 billion years, the Phoenix run is still ascending the red giant branch, while the ATOP run is already on the horizontal branch. So this pace of stellar evolution is being affected by using different opacity calls. Again, this is just one abundance GS98. So this is significant because they are at different stages of their life at the same moment. So two different results using two different opacity codes. So this is something to be noted. Again, here we saw these isochrones, and these are isochrones which are produced with.
Yeah. Those two things don't need to be in agreement.
These two runs.
Yeah.
These should be in agreement, but they're not. There is some difference there, and it will be interesting to look at why they're different. And yeah, these runs are produced with probably, I don't know, 100, if not more, models. So lots of stars here. What? Yes.
Actually, so those two models would be in agreement, but they're models. So why would they ever agree?
Okay.
Yeah.
They want to agree with data, right? So if you have data on those plots overlaid on those predictions, isn't that the point of the calculation to disagree with data?
So these are two different opacity codes. So some people use ATOP, some people use Phoenix.
In other words, if you use the same data, it should be the same plot.
Yeah, these are two different opacity codes. They work a little bit differently, but.
So are those stars data points? You have some.
Yeah. This is the Phoenix run at 12.4 billion years. So it's still in the red giant branch, while the other one, the ATOP run, is a bit faster and is in the horizontal branch. So
the question is, put a real star on that plot. Where does it land?
That's actually meaningless, and the reason it's meaningless is because we can't live long enough to find a star change in this way over that time. So the way that astronomers do this is they do population studies. And so they look at hundreds and thousands of stars in a cluster, and they apply an isochrone, like the isochrone diagram. And the isochrone diagram will then line up one of those, hopefully, will line up with those with the population of stars. Okay. And you do statistics on the population. What Aditya just pointed out here, which I think is very interesting, is that there are groups out there that work very hard to try to date or age or determine the age of various clusters of stars. And this is showing that just by changing the opacity a little bit, you can change the age of a star a lot.
Or their parent age.
yeah, the pace of evolution.
So a single star, but it would be nice, and that would be the next step, maybe a grad student away or two, to then add to do this with the population.
So these are kind of like, in some ways, it's like a climate model. I mean,
in a way, yeah.
Okay, so that's interesting. I was really kind of lost to the experimental data.
Okay, so.
You're about to get to the thing that took you a month to do.
This part, it took a long time to get the script ready on IDL to produce isochrones, because that's a little bit different than producing HR diagrams. Because now we saw the history files. If you want to have a model at 20 million years, it will probably have something like 18.1, 21 point something. It won't have 20, so you got to interpolate that. So it's interpolating those ages, And that took a while. And we also spent a bunch of time on stuff that didn't work eventually. So this isochrone part took a long time. And this is just an HR diagram with those two different stars, which represent where the ATOP and Phoenix fronts are at 12.4 billion years for one solar mass star. And our isochrone data is not as nice as this because we don't have that many models. These are hundreds of models. So we have these different ages, as you can see, 1 million, 5 million, 10, 50, 100, 500, and 1 billion. So these are these different ages and the isochrones here. So this is a Phoenix opacity. This is the isochrone plot with Phoenix opacity table and GS98. If you look at the other one with ATOP, the difference here we see, if you look at this one, the 100 million. So this is this gray-green line. So if you look at this line, ATOP and Phoenix, a little bit different. The other lines are pretty much the same, but these are a little bit different. And this is where the turnoff is happening. So this is where the star is going off the main sequence. It's probably something like I want to say a 5 solar mass star, something like that. That's going off the main sequence, and it's different. So again, it's after the main sequence.
And it has to be really massive. It's the billion, right?
Uh,
Or which one?
it was 100 million. So at 100 million years, yeah, so it would be around 5 solar mass, I think.
More like a pocket. It's not the heaviest or light.
Yeah, it's an intermediate mass star. So yeah, that's a little bit different, which means, something, again, the same thing as before, after the main sequence, after the turnoff, in the giant phase, things are getting different. Yeah, so these two diagrams are a little bit different there. So this is a data. So this is, I think, isochrone plot with ATOP and Phoenix. So this is at 558 million years. So these points depict the stars. So this is, for example, something like a 0.5 solar mass star. This is like 1, 2, and this would be something like 2.2. So these are different models. Here we can see something close to a 3 solar mass star. Once it gets to the red giant branch, they are very different. So again, at a certain point in time, they are getting different, and it's again the red giant phase. So yeah, so something that can be done after this is to look at why they are different again in those in the red giant branch, and also during the stellar pulses in the asymptotic giant branch. So that would be the so conclusion, obviously, from all this is that main sequence, as we saw, is not that significantly affected by doing this, by producing opacity tables using different opacity codes or using different abundance sets. The red giant branch can deviate, as we saw, can deviate considerably after the turnoff. The stellar pulses also are deviating in the AGB part. And using isochrones, we know the pace of stellar evolution is being affected by using different opacity codes. So this will be the conclusion from this. Future work would be to investigate the deviations in the RGB and the AGB type stars for different abundance sets and opacity codes, why they are doing these different things. Also looking at why the pace of evolution is being affected that we saw in the stellar isochrones. So these are something I'll be looking at next in my research for my thesis.
Are you stay here for your graduate?
I'm graduating this fall.
He has 2 months to do all that.
Now, is this undergrad or grad?
This grad.
Grad. Okay.
Yeah.
But you're going to continue on to study what? For a doctorate?
Yeah.
Okay.
Well,
A year?
not yet. I don't know yet.
Or? Usually they let you to move on. That's always what they did in chemistry. You have to go somewhere else. So get the hell out. Sorry.
Okay, yeah, so this is what I would do next. And yeah, well, in the end, I would like to thank the Hallschneider family for this fellowship during the summer. The last semester for me was not particularly a memorable one. Got COVID and took a month out of everything, classes, research. So I was a bit behind, and that provided me with an opportunity to do research over the summer. So really grateful for that. Want to thank the physics department, everyone, all the professors, all the fellow students for their support. In particular, Dr. Ferguson. He regularly met me during the summer, discussed things, and has been very supportive and patient even when I made a few blunders. And I want to thank Lynn Buckley. They were the only other student in the astrophysics group, and they helped me a lot with MESA, advice on IDL, and just general advice on other things. Also want to thank my roommate Virgil and my ex-roommate now Shreyas, who works in Dallas now. So they helped me a lot with the programming stuff as well, with the scripts used in IDL. So also want to thank them. And yeah, that would be my presentation. So thank you for all being here, for coming here, and also the people on Zoom. So thank you.
Thank you, Aditya. We have time for a couple of questions. If you have a question out on Zoom land, please unmute yourself and let us know.
I have a question.
Yes.
So with the isochrones, have you considered, or would it be computationally feasible to do enough of those that you could create an animation of watching some of the stars just go zipping off and seeing the population diminish to the smaller end?
With the isochrones, I mean, you're talking like that movie file.
Right, have, you know,
Yeah.
1,000 movies instead of 5.
So
This is when Dr. Figgy plugs fails. Times 10.
yeah, I think we're looking at something called MIST. Yeah, that was MESA, isochrones, and stellar tracks. So the MIST was basically, I think, a Python code, which would automatically produce these isochrones. So we didn't have to plot them in IDL or anything. It would automatically do that. And what you could do is you could just input all the masses. So one solar mass, 1.1, anything. And it would automatically do that for you. So you don't have to keep changing masses.
Well, it would create scripts. So you
Yeah.
can run them.
Yeah.
And then you've got to graph
So,
them. And,
right. So it is producing. Yeah, it's too much.
Oh, no, it's
Yeah,
done.
Oh,
Yeah.
Cool.
But that didn't work eventually. Some,
Yeah, this was over the top.
yeah.
It was accurate.
3.
Oh, yeah.
By the way, I'm the Exceed Campus champion of the resources to Exceed, which is basically.
I was actually thinking when we were planning to use MIST that it would be a good idea, but that didn't work. So because that on Stellar, which I'm working on, would take weeks, that kind of run. So Bearshock would have been a good idea, but eventually that didn't happen.
So that's a problem for the next grad student.
Probably, yeah.
I guess the other thing is, let's get the pandemic over with, so we're
Yeah.
not having to take breaks and having to deal with crises over and over.
Yeah. We'll probably be losing twice as many people when it's ultimately said and done, or maybe 3
Moving
times.
on, moving on.
So let's-
Sorry.
I want everybody who doesn't have a vaccine to come go get a vaccine over there.
Yeah.
August, I have one other question. You mentioned MESA as a one-dimensional modeling code. So basically just the radial direction. And
Yeah.
we assume everything is spherically symmetric.
Mhm.
What is lost by making that assumption? Is there any desire to go beyond one-dimensional models, or is that?
There are 3-dimensional as well, 3-dimensional models, but they probably computationally, I think they would take much more time, and you cannot do a lot of stuff on that you can do here. So it's an assumption that everything is spherically symmetrical, but you can do a lot more stuff here, and it's pretty accurate.
Yeah, 3D codes do exist, and they include the magnetohydrodynamics, and they include the rotations, and they do all that kind of stuff. The difficulty is is to do that computation, you have to lose accuracy in, say, the nuclear networks, or you have to lose accuracy in the capacities, or you have to lose accuracy in winds. So you have a balance there, where if you want to include a lot of nuclear networks, you might want to use MESA, for example, to look at that. It's nigh impossible to get MESA to go supernova. It just won't do it. It will get really, really close, but it's not designed to do that. It's designed to model, you put in mass, you got L and D.
Okay.
Yeah.
Any other questions?
I had one. Are there any outlying or odd circumstances in which the interpolations maybe yielded something abnormal or didn't seem right?
Yes, actually, when I did the interpolation, one important thing was to, so for example, if I want the isochrone plot at 100 million years, an 8 solar mass star is never going to go 100 million years. So it will die out something like 30 odd million years. And after that, if it's extrapolating that data to 100 million years, that's completely wrong. It shouldn't be doing that. So I just removed those certain things. So if it's greater than that, it's removed from the plot. It's been,
Points.
yeah, removed some points. So that way, something, I had that, but then I had to remove it because that makes no sense because the star has died out way, way ago. Yeah, so some data had to be removed.
All right, any further questions? All right, maybe that's it for today then. Thanks again. And